Here's a challenge. I hand you a 50 by 50 symmetric matrix and ask, how many of its eigenvalues are positive? Solving the characteristic polynomial means finding the roots of a 50th degree equation. That's numerically catastrophic. But what if elimination, the very first technique you learned in linear algebra, already knows the answer? Let's start with two key ideas. First, a pivot. A pivot is a non-zero entry that appears on the diagonal after Gaussian elimination. For a symmetric matrix A, elimination factors it as L times D times L transpose, and the diagonal of D holds the pivot, namely D1, D2, D3, and so on. Second, an eigenvalue. An eigenvalue is a number lambda that satisfies the determinant of A minus lambda, I equals 0. Eigenvalues describe the stretching directions of the matrix, and we can mark them on a number line as lambda 1, lambda 2, lambda 3. Notice how different these two ideas are. Pivots come from row reduction. Eigenvalues come from the roots of a polynomial. Two completely different computations. And yet, for symmetric matrices, these two sets of numbers are secretly linked. Here is the sign theorem. For any symmetric matrix A, the number of positive pivots equals the number of positive eigenvalues, and the number of negative pivots equals the number of negative eigenvalues. This is Sylvester's law of inertia. The signature, meaning the count of positive and the negative entries, is preserved by symmetric elimination. Symmetry is essential here. Drop it and the theorem fails. Keep it and the pivots act as a sign detector for the spectrum. Let's see this with a concrete example. Take A with rows 2, 1, 0, 1, 3, 1, and 0, 1, 1. Notice it's symmetric. Now run elimination. The first pivot is 2, sitting in the upper left corner. To clear the entry below it, subtract 1/2 of row 1 from row 2. The 2, 2 entry then becomes 3 minus 1/2, which is 5/2. That's our second pivot. Continue down, subtract 2/5 of the new row 2 from row 3. The bottom right entry becomes 1 minus 2/5, which is 3/5. That's the third pivot. All three pivots, 2, 5/2, and 3/5, are positive. The actual eigenvalues computed separately are approximately 3.88, 1.65, and 0.47. These are different numbers from the pivots as expected, but notice, all three are positive. The signs match exactly, 3 positive pivots and 3 positive eigenvalues, just as the theorem promises. One more sanity check. Pivots are not eigenvalues, but their products agree. Multiply the pivots. 2 times 5/2 times 3/5. The 2 and the 5 cancel cleanly, leaving 3. Now multiply the eigenvalues. Approximately 3.88 times 1.65 times 0.47. That also comes out to about 3. And both equal the determinant of A, which is 3. So pivots and eigenvalues share two invariants, their product and their sign pattern. Beyond that, they generally have nothing else in common. That is the precise sense in which they are linked. Now for the payoff. Let's compare the costs. Elimination on a 50 by 50 matrix takes roughly n cubed over 3 operations. Plug in n equals 50. That's about 42,000 operations. Milliseconds on any laptop and numerically stable. Finding the roots of a 50th degree polynomial, by contrast, is famously ill-conditioned. Tiny errors in the coefficients produce wildly wrong roots, impractical. So if you only need sign counts, how many eigenvalues are positive and how many are negative, pivots win by a landslide. Here's where this idea becomes really useful. It's called the shifting trick. The eigenvalues of A minus C times the identity are exactly the eigenvalues of A, each shifted down by C. So if I run elimination on A minus 7 times the identity, and I find, say, 4 positive pivots, then 4 eigenvalues of A lie above 7. The pivots of a shifted matrix locate the eigenvalues. We've turned a polynomial root finding problem into a series of cheap elimination calls. Watch this in action. First, probe at c equals 0, count the positive pivots of A. Suppose we get 3, that tells us 3 eigenvalues exceed 0. Next, probe at c equals 10, count the positive pivots of A minus 10i. Suppose we get 1, so only one eigenvalue exceeds 10, which means 2 eigenvalues live between 0 and 10. Now probe at c equals 5. Suppose we find 2 positive pivots. That tells us 2 eigenvalues exceed 5. So one eigenvalue lies between 0 and 5, and one lies between 5 and 10. This is bisection on the spectrum, powered entirely by elimination. This is exactly how production eigenvalue solvers work. Libraries like LaPex use shift and count strategies, not blind polynomial root finding. The sign theorem isn't a classroom curiosity. It's the foundation under industrial linear algebra. And one warning, shifting changes the matrix, but predictably. Each eigenvalue moves by exactly minus c. That predictability is precisely what makes the trick work. Let's step back and see the big picture. 3 pillars of linear algebra converge right here. Elimination gives you pivots. Determinants give you the product equality. And the characteristic polynomial gives you eigenvalues. For a symmetric matrix, all 3 speak the same language. Pivots and eigenvalues share their signs, and they share their products. That single fact links week 1 of the course to the final chapter, and it powers the eigenvalue solvers running everywhere in scientific computing.